Yeah, oh, yeah, yeah, I was
Shit, this is the
thinking of
wrong,
that,
I got the wrong USB drive in there, damn it.
That's all right.
I think.
Supposed to
Well-
have clear skies tonight?
Yeah,
And tomorrow.
I'm ready.
I know you are.
Yeah.
And I do have a bit of an announcement to make at some point in time, so.
Okay.
Whenever Doug is ready.
Whenever.
Well, I'm
If you
still
want me to
getting
go
my-
ahead and just do that now, it's already a few minutes after, and it'll give you a little bit of time to prep.
Okay. If we wait until the
Please do.
video's going in case
No,
the
we
whole
won't do
crowd
that
wants to.
online.
Are you announcing you won the
We
lottery?
got the
Yeah.
mirror.
That's right.
Yeah.
You're close, you're close. Let me read this to you.
Is it
And
good or bad?
it's kind of depends on how you look at it, but I think it's actually better than what we have been dealing with. Okay, this is from Gordon, who's working on our mirror. Things have improved quite a bit for me. My injuries are much better now. Plus, I've gotten a helper to assist with lifting and moving and all this other stuff. So we've gotten back to work on all things. And I finally have some good news for you. Your mirror is ready to head to the coating plant.
Cool.
We'll be doing some small housekeeping things like cleaning, edging, and packaging while we wait for your check for the remaining balance of $9,800. As before, our address is da-da-da. And could you please let me know what your shipping address will be? The mirror will be fairly large package, something over 100 pounds. Best regards, da-da-da.
Ta-da!
So is his address on there? I don't know if I still have it.
Yes.
I can pull up some old emails.
Yes,
So I'll mail the check, was it 9,800?
yes.
And then you want it mailed to your
I'm gonna
house?
turn
Yeah.
off some of the lights, just to.
I think that's the easiest.
You wanna write your address on that piece of paper?
No.
And then I can send them the check
You
tomorrow?
know, if you happen to have access to, a group IO, you might be able to hook up.
Oh, I can do it, but I don't wanna mess it up. I have his address, I can write to his
read my
house,
writing.
but I just
brought
wanna
that.
make sure
Yeah,
that
that'll-
our
To help with
Yeah,
the,
it'll-
mirror's not
I can
at
actually
his
use that.
neighbor's house at Scranton
So I
going,
can
what's
use
this
that.
big
That
thing?
will not guarantee anything. Even if you
No.
got the right address, it may still end up.
Yeah.
Of course,
All
in
right,
Scranton, they may say, hey,
are we
maybe
live?
we're in this place.
Yeah.
Okay, well, welcome everybody. Welcome those of you, is anybody on?
I don't know.
Remotely? Anyway, if you are, welcome. Sorry I'm late. As I mentioned, I decided to come on Highway 24 instead of on the interstate because I was on the side of Manhattan there. It's easier to get to Highway 24, which normally it takes exactly the same amount of time, plus or minus a minute or two. But tonight, because of a road construction, it kind of a little behind the time. So my apologies for arriving late. Any announcements? I know we just had a pretty major one. So the mirror is figured.
The mirror is supposedly figured, it's ready to go to the coaters. Now,
Okay.
the coaters are gonna take how long, I don't know. And what coater, I would be interested in knowing which one, and I'm gonna quiz him on that and find out. Because there's some coaters that I don't think have a very good reputation. And I'm gonna find out who's doing what. Now, we also have the question, do we wanna do this? Do we wanna send as soon as the mirror gets in, just ship it back to Indiana to have Mike Lockwood do a test on it?
Does Mike do coding?
No, he doesn't.
So
He
the-
sends it
Just
out
tests
to-
Where we did our last coding, is that where you'd like for them to?
Actually, it was Ostakowski, something like that. And they seemed to do a fairly decent job. That did on mine. The one that we sent the 27-inch off to is no longer available.
Well, I think we send it to the best coder you
Yeah.
know,
Yeah.
and that we go ahead and send it to make sure it's figured right. Now, I don't know how far you are on the progress of the cage.
See, I don't have it, here's the thing, he's talking about sending it to a coder that he deals with.
Right.
Okay, so I'm gonna find out from him who that coder is, just to make sure it's not one that I think is on my bad list, or my list that I don't think.
That
I'm
would have
very
extra
good.
money in the grant, I believe, that we can,
Yeah,
well, do we, maybe $300?
oh, we have plenty.
We have more,
We have-
maybe I'm thinking of the
I haven't
cubic
used
grip.
near I don't know, $3,000 that I had put in there for
Okay.
rework on this.
Oh, wow,
Okay, the second thing is, I've been working pretty steady on the mirror cell, the back end, who's gonna hold the mirror. It is basically done, except now I've gotta tear it all back down and paint everything and then put everything back together. Okay, so that's gonna take a little bit of time. And if somebody wanted to volunteer to paint all this stuff,
Are you hand painting it or spraying it?
spray paint.
And the sanding,
Right
can
on.
that be done with a electronic helper? Like
Sure.
a
Oh,
handheld
sure.
sander?
Sure, oh yeah. all
I can
this
come
stuff
out and
is
help,
fine.
I can help do that.
So anyway, that part should be ready within a couple, 3 weeks. Now, the other part, the mirror, or the camera holder, the diagonal, all that stuff. The way I'm gonna approach this is I'm gonna get the camera holder put together first, and then and then I'll develop the rest of it after the camera holder's in place. Then I'll put, in advance of that, I'll put a place that I can put a diagonal, take it on and off as needed, so.
Do we want this guy to check the configuration before we do the coding? Because if we do it after, then we've
Well,
got to.
that would be, in that case, I'll have to contact, when we ship out this money, we'll just tell him that, and you know, the thing of it is he's liable to pay for the coating, because that's part of his package. So now if we say, well, don't coat it because we're gonna send it to our coater, then he's gonna be, he's gonna be
Yeah.
making like a
Does he
bandit.
offer any kind of guarantee on the configuration?
Not that I know of, not that I've seen.
Does he send any
He
specs
doesn't.
on it?
I don't think he does. I don't think he sends any test results, any of that stuff. I've not seen anything where he said he'd do that.
Does he answer the telephone or?
No,
He's got a
It's
good little
recorded.
thing going there.
he does.
Well, you know, it is fly-by-night telescope, so.
He's actually got a whole line of telescopes that he sells, and he's been doing this for 25 years. So while he's not very current on his kind of resources,
But he knows.
He's
What would
got
you
his-
estimate the cost of coating it with the guy you like?
well, Ostakowski,
I don't remember the Tombows cost. It's like 1,800, something like that.
it was
thought it was like
15, and then, but we added another, I don't know, 100 or so.
Yeah,
they
because
had
of all the
difficult-
nickel they had to get.
Yeah, they had to take that off, and it took an extra day, so.
So given inflation, it would cost us, let's say, $2,000,
Right.
which you're saying we have in the grant. So if he,
Well, okay, that's gonna be close. I mean, I don't know that we've got that much left, but we've got close to $2,000, but we're gonna end up using all that for that purpose, if that's the case.
okay, well, I'm just trying to figure out if we.
Yeah.
If we have them check the configuration of our mirror,
Yeah.
do we do it before or after the coding?
Well, I don't know, other than just confronting this guy and saying, hey, are you gonna provide test results? If not, we would like to get it tested prior to coding. So ship it to someplace, get it done, and then ship it to our guy that we want to test it, not anybody else. Because I trust Mike Lockwood. I think he does a really good job. He's got a super rep, and a lot of people have said that he's done a great job. So, and he was the one that redid my mirror, and I'm just pretty happy with it. Anyway, point is, we'll have to work out some I don't know how the hell we're
Logistic
gonna do that.
issues.
Yeah, because he's liable for the coating. Now, we could, maybe what I can do is I can say, well, we'll ship it. Once it gets here, we're gonna ship it to Indiana, we're gonna get that back, and then it'll be ready for coating then, and then he can send it to his, provided his is not on the list of
Bad guys.
Yeah, so it gets
So,
complicated real
It seems
quick.
if we don't get it checked, every time we have a problem, we're always gonna wonder,
Yeah, right.
why isn't this
We
thing
don't-
culminating?
yeah,
Why
we
are
don't need a
getting
Hubble.
this?
And I'm
We don't
guessing-
need a Hubble.
I'm guessing it will cost us
I can't
$400 to
I
get
wouldn't
it
take one.
tested, and
James
maybe
Webb's
another
doing really
$150
well.
to $200 for shipping.
Results are coming
That's
in
my
just
estimate.
right on the
To me, it's a
money.
big enough deal too.
Yeah. I
That's my
agree.
vote, is we do it.
I agree. Anybody else?
Thanks. Kind of an, yes.
Because I'll approach him with whatever we need to do, so.
Mhm.
So we need to get hold of him quick before he packs it up and sends it off. Well, he's waiting on our check.
He's waiting on our check, so
Okay.
he's not gonna do anything until he gets his check, so,
Okay.
Yeah.
which I thought gives us a little bit of.
Yeah, it gives you some leverage.
Wiggle.
You want me to mail the check tomorrow, or are you gonna let me know when to
Hold
send the
off,
check?
let me contact you and let you know.
Mhm.
Because I wanna contact him first tomorrow, and it may
Get the
be
specs.
days before we get back, he gets back to us, who knows?
Yeah,
So-
if he,
And
yeah,
I
if he
don't
can
wanna send
provide
the
the
check off
specs,
until
then,
he's come back to us and said, this is what we need to do.
If
Yeah.
he provides the specs
Yeah,
and sends them to you, and you go, okay, that's good, then we can avoid the recheck.
right, I think so,
But we want the configuration results before you send it
yes,
off.
yes,
Mhm.
yes,
Unless he fudges the results.
yeah.
Sorry, Doug.
And if he
No, no.
fudges the results, then we'll know, and then we're really gonna go after him.
Mm-hmm. Yeah. Rubber band guns and everything.
Yeah.
Okay, well,
Mm-hmm.
Thanks for the
My
update.
answer.
It's good to hear there's progress, you know,
Mhm.
considering that it seems like there hasn't been for a while, so. Any
it's been
other,
ongoing for a long time.
any other announcements for the general good?
Sent an email out to everybody in NECAL asking them to sign up for duties, which you got right there.
Crickets.
Yeah.
Okay.
So anyway, here's the
It's only
upcoming
been an
events.
hour.
Again, probably everybody already knows this that's here. These are of course, the public events. The next public night is June the 18th. Of course, the next member night, and the first one in a while,
Yes.
is this Saturday. Unfortunately, I'm not
pre-pandemic,
sure I'm going
yes.
to be able to make it, but
Mhm. I'm planning to
if
be
you
there.
can, then
I
that
never
would be
had
a
use the scope anymore.
that would be a thing. As far as that public night goes, this is something we've had quite a few conversations about lately amongst the board and others. And as Dave mentioned, he sent out a thing here with trying to get some response on that. Have you heard anything from anyone?
Nope.
I'm kind of happy to do what I can. I thought
Mhm.
possibly, here's the thought. We've talked about having some sort of a theme, right,
Mhm.
for these things, and it's going to be hard to cobble together a theme between now and June 8th. Well, maybe it wouldn't be. Also, I think we realize that we don't have the moon that night, which kind of makes for a pretty obvious theme. But if we could come up with maybe just a list of objects that would be something worth interesting to look at, and then we could make a little presentation about those, something along the lines of, you know, here's what you're going to see. This is I don't know, some galaxy M something, right?
Mhm.
Whatever, and say, you know, it's called M this because it's in this catalog. This guy made this catalog
Yeah.
because he wanted to find comets and
And
didn't
got
want to
tired
get
of seeing
distracted
them,
by
yeah.
things that looked like comets but weren't. And show them a nice picture of it and say, okay, here's what you're going to look like. It's going to look a little different in the eyepiece, but you're going to see it live. I would be happy to kind of work on that stuff.
Okay, I'll put you down.
Uh,
And then in that email, I included sky charts, and I spent some time figuring out what's up. And so you've got several of your bright stars that are also double stars.
Yeah.
Yeah.
And then you have most of your Messier objects are clusters.
Okay, yeah,
So-
stuff, I think stuff like that where we could just, you know, have a list of objects that we're gonna put scopes or eyes on, and
This is for
kind of give a
them,
little
right?
bit of a background, you know, this is
Right.
what you're gonna see. You know,
No
if we could
problem.
look at, I always have to kind of filter this because, you know, there's what I think is interesting and then there's what everybody else thinks is interesting, but if we could put like a Cepheid up there and talk about distance scales and stuff like that, you know, I think that sort of stuff's
That
sort of
could be the
interesting.
presentation.
Yeah,
Yeah.
and you know, this is how we figured out that galaxy is that far away.
So
I think that makes an interesting story. I think we need to kind of pitch it to where it's not going to be, you know, like we're going to start talking about Eddington's valve and all that kind of crap, but tell it in a way that makes it understandable that, you know, this was a really important thing for understanding the structure of the universe, really. And it has a neat history, you know, the women at Harvard that figured all this crap out. You know, it's an amazingly interesting story to me. Again, I always have to remind myself that what interests me and what interests others is not necessarily always the same. But so those were some of the thoughts I had, and I would be interested in hearing comments or
The thing is that, you know, you don't know for sure what somebody's gonna be interested in if it's something they've never even heard of.
Well, and
that's just the thing, is you open it up to a number of different things and people will say, hey, that's cool. And they didn't know it was there before. That's one of the neat things about astronomy, there's always something else new out there.
You've got to start at some level is the problem, and you
Yeah.
don't know what their level is.
And maybe just try to kind of weave in several levels. I mean, you know, we had a couple
Yes.
the other night, we had a couple little kids out there, and I was not really sure what to say to them.
Get out of here!
Hey,
Other than,
That's usually what I
other
say.
than, you know, please stop running around and.
Well, we had that live, thank you. Forever recorded.
You know, and I did learn a lesson, because when we were kind of, you know, when I was sort of giving them a little tour, the one little girl almost tipped the old mirror over. She said, "Ooh, what's this?" And she pulls this mirror that's got to weigh, what, 200 pounds? Almost over onto herself. And I'm
Yeah,
thinking,
well,
crap, you know, we got to. And, you know, these were good kids. They were certainly not. But, you know, it reminded me that we need to kind of keep track of things.
We need to find a home for that. I don't know how long it's gonna be.
Yeah. But
before-
I
before
thought it was
Kate takes
fun.
it back, if ever.
I thought it was fun to have, you know, a mix of ages and all, but I was, you know, just at times like, oh gosh, you know, what do we say to?
So I was gonna do the
Kids.
binocs and planisphere, just cause put my money where my mouth's been running. And mostly there's some bright stars, link it to some constellations, and I did buy a box of mini, what do they call them, the glow sticks, small size,
little silent
red
things.
glow sticks, cause if they have to look at a planisphere, they may not have a red light, but a little
Yeah.
2 or 3 inch glow stick. So I bought a box and there's like 200 in there.
oh,
Okay.
So I figured everybody could have something, at least when you're in the dark, you realize there's a person there, or if they have to read something.
Okay.
But, and something for the kids
Yeah,
too.
good.
So, got that.
Those are
And,
just kind of inherently fun too.
I mostly, I think the stars that were in my email will
And
be
when did
them,
you send
and
the
some
email out?
constellations, sent it a day or two ago.
oh. I have to
Well,
check.
maybe-
It was
Well,
to the
I'll do
group.
constellations and also I can, you know, in the constellation thing, I can also bring up the
Right.
stars.
So we
and
could
then
all
find
kind of
out,
hit
yes.
that same thing, because there isn't much out that night.
Right.
Other than those objects. Did you guys get this email? 'Cause
Yeah.
haven't had
I
it
did.
either.
Yeah.
I just
Okay, you
finally
got it.
opened it today.
Oh, okay.
Well,
Yeah.
maybe,
Now.
and maybe over the next, you know, couple of weeks or so, we can kind of come up with a tighter list of the things that we want
Right.
to look at.
So Janelle on constellations, Doug on classroom.
I'll be on the pad.
You'll be on the pad, maybe with the meat, 8-inch.
Yep.
And then, if you even brought your scope,
Yeah,
if
I'd
it
bring
happens
both
that
of them.
they go, maybe somebody else in the club, you could be next to you and you can kind of let them experience your scope.
Yeah,
Yeah.
Is there a possibility we can get that new scope of Dan's?
It is. I thought at member night, I will take out whatever adapters I found at Dan's house and see if
Oh.
that thing can get fired up. Now, I don't know anything about equatorial mounts. So somebody else is gonna have to,
Well, you know,
Well,
that's
you
one
don't know
of the
anything
things.
about German equatorial.
Right.
German, Spanish, French, I
Yeah, you're 16
Taiwan.
inches equatorial.
Yeah, the 16 inches in equatorial.
don't know. Yeah,
It's the
but
fork.
the things sticking out and
Yeah.
polar alignment, it's too complicated.
You know, that thing I had about
Those weights will
member
hit you.
lights, that's one of the things, try out new.
Yep, let's
stuff.
get that sucker fired up.
Yeah.
Let's get going.
well, yeah, and the
Do some stuff.
8-inch, yeah,
8
I'll be
inch.
out,
Let's unpack that sucker, see what we need to get it going. And
because I plan on being out there probably
daylight?
I
6.
I can guarantee you're gonna need a 2032 battery to replace that one that's in there.
The little button, 2032.
Yeah.
Yeah, the big, well, they're a
They're the
big.
bigger
They're big.
That's a
outside,
BA.
Nickel
Yeah.
quarter.
That's those
sorry.
ones that are about this
A
big.
BA 2032?
About this big.
2032, yeah.
Oh.
CR 2032.
Yeah,
CR,
CRs.
yes.
Yeah.
I think they've got a bunch of them.
I think so, I think we've got some out there now.
Mhm.
Any
Okay.
more than,
I'd be happy to help out wherever you guys can use me out there.
Okay.
A lot.
You can go through the bottom.
Constellations
Make
or
copies.
presentations.
Yeah.
I can make
Not the
copies.
front.
Yes, we
I
figured
guess
out a better way to do
people-
that.
Well,
Not a
and
problem.
Angel, if he ever connects, he's offered to be a greeter
Okay.
Mhm.
Yeah.
at prior meetings.
Mhm.
And given what I think you are interested in, helping Janelle or
Sure.
Atoscope kind of seems to
I've
fit
not
you.
usually, I've not worked the scope, I don't know anything about it.
Well, there you go.
I
Now
can
we-
BS with the best of them. And I do my
There you go,
calculations,
that's my,
but I can
that's
also
my.
learn to do
That's
the
scope
key.
also.
That's
So
the
I'd
key
be
skill.
happy to learn.
This,
Thank you
this,
very
it's,
much.
it's really, it's gonna be really fun. I think we
yeah,
can get this
I
thing
mean,
going.
the one thing it'll be a little bit inconvenient is that that's almost the solstice. So,
Well,
you know,
that's-
it's gonna be a
yeah.
late, it's gonna be a late night.
Yeah, it
Right.
is. But you know, some of the stuff, just the sort of background stuff you can do when it isn't that dark yet.
Right.
It's just that it takes forever to get dark in the summer.
Yeah, and that's maybe something, you know, we can kind of talk about stuff when it's still a little bit light. But anyway, any more on that we wanna, so it sounds like we've got some people lined up for filling the various slots.
Is anybody online, Russ?
Yeah, two people.
Hi, people online.
Hi. News.
Yeah.
I rounded up a few things. One of them is this potential meteor shower outburst, May the 30th. This was a comet that
Yeah.
broke up, Schwarzman
breaking up.
Bachmann or something like that. Yeah, Schwarzman Bachmann. From what I've been able to read on this, it's like it's either going to really be something or it's going to be absolutely nothing.
Yeah.
Meteor showers are like that.
Yeah, and hopefully it'll be something. So this will be May the 30th. Hopefully we'll have some clear weather if there is something.
There's still a principal body of this of this 63 or 73, by the way.
Okay,
Uh,
and this is not a new
No,
thing,
no,
right?
it's been through many returns.
It
Yeah,
just-
it's
it
just
fell
that
apart
just that
this
this time
time.
it happens to be
Well,
falling
it's the
apart.
73rd periodic comet
Yeah.
that was discovered, so it was long ago.
Yeah. So anyway, this will be in Hercules, radiant. So anyway, I would point to that direction, except I don't know what direction I'm facing right now. So anyway, so this should be, we hope, interesting, fun to watch. Find a nice dark spot. This is one I thought was pretty cool.
Oh,
And this is I think the more I delved into this, one of the oddest stories I've seen in a while. This fellow who was originally identified as an amateur astronomer thinks that he found the source of the so-called WOW signal. If you've never heard of this, this was something probably in the mid-60s, I think. This has been quite some time now, that a signal was received at a radio telescope at Ohio State. Very powerful signal, and you know, they were so powerful that when they were looking at the printout, that's what all these old kind of alphanumeric characters are, intensity signals, and this one was so powerful that somebody circled it and went, wow. And so it became the WOW signal. And for the longest time, nobody really knew what the source of it was. Never really been observed again. I think the telescope that observed this was torn down years ago. I think they turned it into a practice football field, which it's Ohio State, so I guess that's how things work. Anyway, now this, and one of the reasons this was interesting to me was, you know, last week we talked about data mining and looking through databases, and that's essentially what this person was doing. When I dug into this story a little bit more, it turns out that the person was identified as an amateur astronomer. He's actually a professor, which is always a bad sign. And he's a professor of, I believe, studies like conflict, and an amateur astronomer as well. He's not just a completely, not just a completely unknowledgeable person, but he wrote a paper that was published in the Journal of Astrobiology, which I didn't even know existed, basically estimating the number, and it was unrelated to this, estimating the number of what he called hostile extraterrestrial civilizations. Anybody else see this? And using analogies with conflict on Earth,
Yeah.
coupled with understanding of like how many exoplanets there are and stuff like that, he came up with the conclusion that there are 4 hostile, aggressive civilizations out there in the Milky Way. Which, I have not read the paper, but I thought that was kind of interesting. Is like, is that the Klingons or the
Yeah, I was
the
gonna say,
Romulans?
Star Trek got him beat a long time ago.
Anyway,
Until we're secured with warp drive, I don't think it's gonna be an issue.
I don't think it's going to be a problem either, but I just thought, it's a really interesting example of logic run amok. But anyway, interesting story. But this was, I thought, I don't know if this is actually true, if the star that he's identified is actually the source, but it led to a really interesting series of reading for me yesterday afternoon. This is one I kind of liked. This was this Lucy was a probe created by the Southwest Research Institute, I guess. The PI of it is there. It's some millions of miles out. It's actually intended to visit an asteroid, right?
Several Jupiter Trojan asteroids.
Right. But it actually was able to observe the lunar eclipse, and I should probably, I put the URL down here because they actually, anyway, if you want to follow up on this, you can actually see the little bit of video of it, and there's the little fuzzy Earth and the even fuzzier moon, and then the moon disappears, and then it comes back, and it's really pretty interesting actually. But it was this imagery captured from quite far away in space by this Lucy probe. So I thought that was kind of an interesting one. There's the URL if you want to follow up on this. Here's one for Justin, black holes. This one was the Sagittarius A with this telescope that was really they've kind of talked about this thing as if it's some kind of new thing. It's really just a really, really big, very long baseline interferometer as far as I can tell, which, not that that's something to sneeze at, that's a really very interesting thing, but they were able, of course, to image this black hole at the center of the galaxy, which I think somebody, Roger Penrose maybe, won the Nobel Prize some years ago for theorizing that this thing was there, and now there's been an observation of it. Can't be observed in the visible wavelength because the dust between us and them extincts something like 26 magnitudes worth of light. So no way to see this thing visually. So this is obviously not in the visible part of the spectrum.
Is it microwave that they're using?
It's a
Very, very long.
micromillimeter wavelength.
Micromillimeter, okay, yeah.
But this little picture right here was not from the article in Nature. It's what all of the various dishes involved would look like if they were all gathered together in one spot. And that's what this is supposed to be. So each one of these is a real dish. It's just not, they're not all.
That's on the top of the Atacama Desert.
Yeah.
One of them is, yeah.
And of course,
Yeah.
and
No,
from that high, the
there-
Milky
there
Way
are-
was
There are
there's
many.
bunches.
Yeah, oh yeah, there's a ton of them out there. There's this
Yeah.
one out there. There's this one out there that I've gotten really interested in. It's called the Atacama Cosmological Telescope or something.
Yeah.
And it looks almost exactly like the Webb
VLA.
Space Telescope. It's this big
Uh-huh.
triangular. It's almost exactly the same size too, but it's in this bowl.
Yeah.
This metal surrounding, and I was thinking, why in the world would you go to all that? And then I started thinking about the wavelengths that it's detecting, and thinking, there's going to be a huge source of all that. So apparently
You've
they
got to
figured out a
close
way to
off.
isolate this thing in this weird looking bowl, sort of. That was sort of
It was-
fascinating. They just recently tried to use that to find the planet P or whatever the
Planet
planet that the
Nine.
guy at Caltech thinks is
Oh,
out there.
yeah,
Didn't
Orion.
find it that way, but it was an interesting. So anyway,
Just on the right, that image right there, isn't that the black hole that that's the one they found an image right here, right?
Yeah,
Sagittarius
Sag,
star.
yeah, that's
Yeah. I was gonna
Sagittarius.
say,
The other
it
one
looks-
they did
yeah.
was M88.
Yeah, but yeah, I mean, this one you can touch it, or remember
Here.
those little toys kids used to play with the 3 sides? That's what that one kind of reminds me of.
Yeah.
Yeah.
If you looked at,
Different.
if you go to this article, they actually have an artist's impression of what what it would look like if you were closer to it, which I don't think you'd want to be very close to it, to be honest with you, because it would be a terribly high radiation environment. But anyway, so I thought that was kind of an interesting, interesting thing. I tried to find a map of where all these dishes actually are, and
let's
I
see.
couldn't come up with one, but it's.
Atacama.
Well, they're all over the world. I mean,
Yeah.
the whole thing.
Hawaii,
The whole thing with long baseline
Chile.
is it's got to have a long baseline. And,
Antarctica,
It was-
Europe, they're all.
It was an
merged
interesting.
in to get,
Yeah. I was hoping you'd had a map of all of them, but I couldn't. Find it.
EHT,
Anyway.
the Event Horizon Telescope has that map on there.
So anyway,
It's 1.3 millimeter.
did you find one?
Oh,
Let's find the wavelength.
1.3 millimeter.
Oh yeah. So that's
It's pretty
that's
long.
longer. That's longer than
For a
microwaves.
microwave.
So anyway, so this was one. You know, the Webb Space Telescope has become like the glamour child and gets all the attention now. So I thought I'd throw a little bit of love at the Hubble, because it's still up there and it's still working, and it's been up there for a long time now. And this was an interesting one because for several decades now, there's been this ongoing program to image Cepheid variables in various galaxies in order to refine the Hubble constant, right? So, interesting thing there, the Hubble is being used to refine the Hubble constant. And after 30 years, there's been a new value of it, and I should have written it down, but the number that sticks in my mind is 68 plus or minus 0.5, what is it,
Oh, you're starting to.
parsecs per kilo parsec.
Is that just in redshift nomenclature? I mean, are they using redshift values, in other words?
Right, yeah,
And they're
the-
using
Or
redshift
standard-
values
standard candle.
without regard to how many years.
Right, yeah, so what the Hubble constant tells you is how fast things are receding as a function of distance. So it's actually an acceleration if you look at the units of it. It's units of distance per units of time per units of time, I think. So anyway, there's been a whole lot of controversy about it because it's very finely poised between several different theoretical possibilities for what could happen. And so there has been, for years people have been trying to and I think at the time I took, Astronomy 101, the number that got kicked around, I believe, was 73. So that number's been revised downward just a little bit.
It'll probably get to 42 at some point.
42, yeah, because that is the answer to life, universe, and everything.
That's right.
So I probably should have written this down, but I thought this was kind of a fitting tribute to this instrument that got a lot of grief, not the telescope's fault at all. But it's this is a scientifically very, very important. So anyway, I threw that one in there too, just for that. This came from NASA Goddard Space Flight Center, where I spent a summer working on something that had absolutely nothing to do with astronomy. So always interesting to me. I was looking at how light reflects off of plants. Anyway, this is one I kind of liked too. This is at the University of Florida. Scientists grow plants in lunar soil. They were rather surprised to find that this not only worked, but worked really well. And this actually has a lot of implications because, people like Elon Musk and others who want to go live off in the cosmos are going to have to grow food. And right now, there's nobody that's ever really been able to figure out how to make a fully isolated biosphere, which is going to be necessary to do, where you have to create one from scratch, basically, which, I'm not a biologist, but I know enough about soil microbes to think that's going to be a super difficult thing to do.
Just how many potatoes can you eat, though, really?
Well, and you got to have nutrients to. Are you familiar with the Biosphere 2 project? Anybody ever hear about this?
Oh, yeah.
It was this big greenhouse they built basically in Arizona, and these 8 people were going to go live in there. It was going to be fully isolated from.
Yeah,
It didn't work because people don't understand yet how to do that, right? So, and that's a key problem. It's going to have to be solved if
Then
everyone's
they're ready to kill each other. So.
Well,
Yeah,
you know, and it also had this kind of. It was not scientifically rigorously
Yeah,
designed
right.
from a social science perspective. So yeah, that was. But anyway, this was I thought really interesting because it kind of tells you, also tells you a little bit of something about what the moon is made out of, I guess. So anyway,
Part of the Earth.
so these were people at the University of Florida that did this. And this is the 2 scientists that were involved in it. They're both actually agronomists. Actually, they're in their School of Agriculture. I always wondered about these things. These little, are these like rank insignia? Is that something we have to
That's what it
wear?
looks like.
You know.
I don't know.
Anyway,
No.
there's this. There's one of the little plants they grew there. So, anyway.
You know,
Cool-
one
cool
thing
story, I
that,
thought.
when they talk about, establishing settlements on the moon and everything, the thing that always bothers me is when you think about what happened in Antarctica, we set up all these things and then you go over the hill and you see all the trash, that has just been pieces of equipment and everything out there. And I think of that happening to the moon, it just makes me sad.
Yeah.
It just seems like we can't, everything we touch, we ruin to some extent.
Yeah.
Oh, don't worry, you won't be able to see anything after Elon Musk gets these 60,000
Little satellites up
pieces
there.
of debris.
Well, that's true, space link and all that, yeah, that's true.
Yeah, well, who was it? Maybe it was Elon Musk that said he wanted to die on Mars, but not on impact. And I thought, as far as I'm concerned,
Yeah.
if you can get there, more power to you. But anyway, so I thought this was kind of
Interesting,
interesting.
yeah.
Okay, so that's all the news, unless anybody else has got something they want to add.
Well, there is, if anybody is on Curiosity Stream,
I used to belong to that.
there's a new show on there for how the moon is the next way station
Ah, okay.
for
Oh,
going to Mars and
Right.
the rest of the solar system.
Well, aren't the
Yeah,
Artemis
lots of-
flights supposed to start sometime in 3 or 4 years, somewhere along the line?
Well, yeah, because they're getting ready to do the first SLS launch.
Yeah. Yeah,
On it.
they test flew some of the hardware last week.
But this
was
is-
at
this first-
White Sands. They did some tests on it, I think, last week. The first launch system. They rolled it out to the pad and then rolled it back, and I'm not totally sure why that
It
happened.
was fuel system, fuel
Yeah,
tank
some leaking or
system
something.
checks.
But anyway, okay, well, so I thought what I'd talk about tonight came about just from a suggestion I think Dave made, which I thought was a good one, which is kind of just talk about some sort of basic sky stuff. And this may be a bad title after I started putting this together. I don't know how much this is going to be about finding your way. It may be more about just general knowledge of the sky. Taught inside, it seems to me like the ideal way to do this would be to go out and actually be looking at the sky while we did this. But one of the things I kind of thought we might be able to do at some point is follow on to this with a session where we do something like that at a members night, maybe just to, because I don't know about you, but I'm not super good at identifying things. I'm reasonably good at it from time to time. And a lot of this is probably going to be stuff you all know. I kind of was hoping maybe we'd have a few more people who are kind of newer members that maybe would benefit with this. But anyway, the other thing that, the one thing though I did find was I kind of learned a little bit from this. I remembered a few things that I kind of knew at one time and maybe never really totally understood. So I hope this is not a waste of your time, but anyway. So, one of the things that you kind of, we talk about telescopes and all that sort of thing and binoculars and this and that. And you kind of lose sometimes in all that, you kind of lose the fact that it's really just kind of uplifting, I guess, to go out and just look at the sky. But it's also, to me anyway, it's really confusing. You know, and some of my best memories as a kid were we had this really big flat rock out behind our house, and this was, of course, up in the mountains where the air is pretty clear. And I would just go out and lay down on this big flat rock and kind of look around. And I had a couple of books that I would take out there with me. One of them was the H.A. Ray book, my old standby, and then later I got some better ones than that. But I always found out, you know, it's like there's these pictures and then there's that, and you know, hard to tell sometimes. So that was one of the things that sort of made me think that perhaps this might be a topic we'd want to just kind of visit at a meeting. So anyway, first of all, what does it mean to be dark? And this is something that I think we pay attention to a little bit more than perhaps than people who are less interested in looking at the sky. But there's, you know, there's actually more to that, I think, than just the simple, you know, obvious thing that when the sun sets, it becomes dark. And it also, when we talk about the sun setting, that kind of reveals a bias in the way we look at things, which is we're thinking about the sun moving, and that's obviously not the case. So as the Earth rotates, you know, we get into the shadow of it, basically. And it doesn't happen all at once. It happens kind of gradually. So we talk about this period of twilight, and this actually came up in a conversation with one of the people at the public night the other night, you know, what the various kinds of twilight, basically. So there are actually formal definitions of these things. There's informal definitions as well, but the formal definitions of them are that you are in civil twilight when the sun is between the horizon and 6 degrees below the horizon. You're in nautical twilight from 0 to 12, and then you're in astronomical twilight from 0 to 18, and then after that it's dark. And generally, as a rule of thumb, civil twilight, you can still make out features. You can see a few of the brightest astronomical objects. Nautical twilight is actually the period during which you can still see the horizon. You know, that's why it's called nautical, because it was originally a concept from navigation, right? Where in order to do celestial navigation the old-fashioned way with sextants and all that stuff, you had to be able to see the horizon, right? So this would be an example of civil twilight. This, I believe, is Chicago. Yeah, there's used to be the Sears Tower, now it's something else. This would be a pretty good example of nautical twilight, so you can still see a sharply defined horizon there. But you can see a few things in the sky, and then this would be astronomical twilight. I have no idea what that city is, but it wouldn't be a place I'd be trying to look at the sky because there's way too many city lights. I could not find any pictures of this stuff that were not in cities, which surprised me a little. So anyway, those are the twilight zones. But also, I think, you know, there's this really interesting question behind all this is, you know, why does it get dark at night? It's actually, the fact that we have all these twilights is because the Earth has an atmosphere, right? So if you're on the moon, there would be you wouldn't have to worry about all this civil astronomical stuff, right? You would just go from being dark or light to being dark. Because the moon technically, I guess, has an atmosphere, but it's about that thick and right down at the surface. Whereas the Earth, of course, we have our nice, wonderful, deep, oxygen, nitrogen-filled atmosphere that supports life, of course, but also is really, really good at bending and deflecting light. And so we get these twilights because of refraction, right? Because of light being bent by the atmosphere. And have you ever seen a green flash? Have you seen
The sun setting?
Yeah, where'd you see it?
I have not seen
Oh,
those
you-
pictures.
Yeah.
I saw one once, and it was weird because I spent a summer. My mom used to live in the U.S. Virgin Islands, so I spent a summer down there, and I thought, you know, this is perfect. I'm going to see a green flash, and I would sit there and watch the sunset every stinking night I was there, and it was beautiful, but no green flash. And what a green flash basically is, you know, if you can imagine the sun setting into this refractive environment, it's, you know, light gets spread out, right? The green flash looks green because your eye doesn't see red light very well, but it can see green light pretty well. So it's like looking at the side of a spectrum, and you see that little bit of green, but then the red gets lost in a combination of scattering and physiology. So anyway, I never saw a green flash, and then shortly after I moved to Manhattan, I rented a house my first year there, that had a window that looked almost due west. It looked a little bit southwest. And I used to sit there every night and have dinner before I went back to work because I wasn't tenured yet, which meant that I didn't do anything but work. And I was sitting there having dinner one night, watching the sunset out my window, and there was this green flash. You know, of all the places to see it, because normally it's easiest to see when there's a really well-defined horizon. So that's why seeing it over the ocean is more common. And there was this, and you know, it took me aback. But anyway, it's kind of related to this notion of light bending over the horizon and being scattered in the atmosphere and all that sort of stuff. So, so that kind of feeds into this notion of, you know, what does it mean to be dark, and also I think kind of affects the way we observe. Right. One of the one question that both of the kids asked me the other night when we were out at Farpoint was, why do stars twinkle?
Yeah.
And you know, it's such an interesting question because it has answers at a lot of different levels. You know, you can go all the way from, well, it twinkles because there's different temperatures, on up to things to do with like dipole moments and that sort of thing. So it's always, to me, a really fascinating question to kind of answer. Of course, one of the other questions that we come to grips with when we're out looking at the sky is, you know, how dark is it really? And I think we're all, being who we are, sensitive to the notion of light pollution and the fact that humans make a lot of stray light. I don't know if you've ever seen that map of the whole globe, right, with all the lights. And I mean, it's a fascinating map. It's actually one of the ways that people estimate what the population of the planet is. But it's also unfortunate because, you know, for two reasons. First of all, it floods the, you know, places where there's a lot of human settlement, it floods the sky with excess light, and excess light is excess energy. You know, so you think about all the greenhouse gases that are being burned to make the electricity that's just going up to space and getting in our way. I don't really see any quick answers to that. Again, my mom, who used to live in a lot of interesting places, lived for a while not too far from Mount Palomar Observatory. And there was a big stink there at one point because the Mount Palomar astronomers had gone down to this place she lived, was called Dana Point, and they were, you know, essentially asking people if they could put hoods over the streetlights so they would only point down. And you would have thought that people were asking them to give up their firstborn.
Yes.
You know, it's like, no, we want lights everywhere because we like light, I guess. So anyway. So here's a map of, this is actually I think, kind of interesting map because it's divided up into the Bortle levels. So, you know, we have this system that came about, I think, sometime in the 70s, wasn't it, that the Bortle system came into, maybe even later than that?
Yeah, might even be 60s or 50s.
Yeah. But, so, you know, these are, they kind of, it's this system that goes, I believe, from 1 to 9, with the lower numbers being darker. And so we're here. Where are we? Somewhere around Farpoint's like somewhere around in here somewhere, maybe.
I think Bortle will work for sky and telescope.
Yeah. So yeah, there
Yeah.
we go. So 1991, the Bortle thing. So here's the Bortle system here. So this is basically just a way of kind of quantifying in a really, I think, kind of rough but very useful way. So Farpoint, I think, is Bortle 3, right?
Yeah.
Which is not too bad, actually. Bortle 1, I think I've seen Bortle skies. I've been in Bortle sky 1 skies twice. Once was in Arizona, or sorry, New Mexico. I camped one evening at Chaco Canyon, which is, of course, a kind of a prehistoric settlement, and it's dark, so dark. I mean, you literally could not see your hand in front of your face. You could be holding it right there. The other time I was in...
when was that?
That would have been about 2004, maybe?
Because that makes a difference.
Yeah, is it worse now?
Well,
Everything.
just about every place is.
And the other one was, I was at a research site that we worked at in South America. It's a place called Abarcajou, which is a forest, an old remnant Atlantic forest in Paraguay. And I had to answer the call of nature one evening, and it was pure groping to try to find my way, because it was just as dark as you could possibly. And of course, I had not thought to bring a flashlight with me. We'd gone to camp out in the middle of this place because we were told we'd be able to see wildlife, which, the only wildlife I saw were the mosquitoes that were biting me. But anyway, so that was probably a Portal 1 situation too. But anyway, I think 3 is not too bad. Actually, we are kind of blessed to have a pretty good dark sight, although I always envy the people that are, a little further over this way.
Well, and we are starting to lose, we're getting closer to a 4 now.
Well, I was noticing that the other night, that
Yeah.
the sky glow off into the east, and particularly to the northeast, was pretty. I think when we were trying to look at, was it M51, the whirlpool, that one of those things was off that direction.
M13. Mm-hmm.
Yeah, you could kind of see that it was.
Getting that.
Yeah. What is it at your place? Is it probably about the same or
It's
better?
4.
Is it
It's a
4?
4.
So anyway, when people talk about the Bortle scale, this is what they mean. This system of light and dark.
Sorry.
And here's some of the kind of visual,
Oh, yeah.
some of the visual impressions of all this. It's kind of interesting what they see, things you can see. You can see, according to them, the zodiacal light has a color. At Bortle 2, you're supposed to be able to actually see it, and it casts shadows. I think I've seen the zodiacal light here in Kansas maybe one time, but it looked pretty indistinct. It just looked like a cloud.
Well,
basically.
And it
Like kind of triangle.
tapers
Kind of a
up as it
cone, yeah.
goes up.
Yeah.
Yeah, it was evident at Farpoint for many years, and only on some nights.
And
You've got to have a crisp night.
And it's helpful if it's like early spring too,
Yeah,
right?
right.
Yeah.
Or fall.
Or fall.
You could do it either
Yeah,
one.
right, because of this. Yeah, okay, right.
Geometry works.
I don't know, for some reason got interested in the zodiacal light not too long ago, and I was doing some Googling on it, and I came across a doctoral dissertation by a person named Brian May. Anybody know who Brian May is?
Mm-hmm.
He received his PhD in astronomy by studying the zodiacal light. He's also the guitarist for the band Queen.
Oh.
So, you see, and he's you see this guy, and he looks like a rock star, basically, which is essentially what he was, but he's apparently an extremely talented physicist as well, and he wrote his dissertation on the zodiacal light. It's funny, his dissertation is one of the more interesting ones I've ever read, because you can tell he didn't need to toe the academic line all that closely, because by the time he was doing his PhD, he was already super rich from selling records, basically. So anyway, here's kind of a breakdown of the Bortle scale. Here's an overlay of our map here. I think I found this from a website that same light pollution website. You can kind of see, I guess Farpoint would be what, around here somewhere, maybe?
Yeah, that little dot right there is Auburn.
That's Auburn. So Farpoint would be about like right there then, maybe, somewhere around in here.
Yeah, right around.
So you can see it's, as by local standards, we're actually not too bad. You get some really pretty nice dark sites out in the western part of the state. But yeah, this this whole blob of light right here, makes it tough. I know when I want to go out and look at things in Manhattan, I usually go to this place called Top of the World, which is just sort of on the edge of town. It's a hill, and it's gotten noticeably dark, noticeably less dark since I've lived there. And of course, I've lived there for close to 30 years now, so it's not a short amount of time, but I've just been able to see difference in that amount of time, notable difference. Okay, and that actually also brings up something else that I had a conversation with someone with the other night, and it's about seeing light. And again, I know you probably already know this, and I was kind of hoping maybe that we would get maybe some of the newer people just to kind of, provide basic background information. But we see light basically a couple of different ways. So if you kind of were able to look at the back of your own eyeball, which of course you can't do, but if you would, you'd see that there's two different receptors back there that are sensitive to light. Some of them are called rods because they're sort of rod-shaped, and some of them are called cones because they're sort of cone-shaped. The rods see light and dark, basically. They are mostly sensitive to intensity of light. The cones are more sensitive to color. And so if you're trying to see things at night, you're mostly relying on these cones. And if you there's a little more simplified look at this, the rods, they tend to be kind of on the edge of the retina, the kind of sensitive optical, photoreceptive optical surface. And the cones are more or less right behind the lens of your eye. So this is the reason why most of you, I'm sure you all are familiar with averted vision, right? If you want to see something that's very faint, you kind of don't look straight at it. And when you don't look straight at it, what you're doing is bringing these rods into play. The rods, though, they don't differentiate color very well, but they do a little bit. And they're very, very insensitive to red light. They're more sensitive to green and blue, very insensitive to red light. So that's the reason why, if you want to maintain dark adaptation, red light is what you need, because it doesn't kind of force that physiological response to light that the way some other wavelengths do. So, this is the reason why we use red light.
And I remember hearing it explained once on, in when you do biology and especially like cellular and whatnot, they look at this and then they say, well, why does that make sense? Well, one of the best ones, and I use this sometimes when I'm talking about it, is that if you were, a caveman out someplace, and the fire's starting to die down and everything, and there's some kind of a bear coming up from the outside, coming around over there, the rods toward the outside are going to pick up that dark change, the movement kind of thing. Whereas during the day, you're looking straight ahead at whatever it is that you're looking at. But the rods are, since they're on the outside, they are better at detecting that kind of motion.
Yeah.
And that really does make sense. That's why, averted vision, you see it over there kind of to the side. Well, it's the same kind of thing. And it all kind of makes sense. To me, it's always kind of interesting to try to figure out why things are the way they are.
Yeah, and I don't know if it's true or not, but one of the stories I heard about why we have two different kinds of photoreceptors is that the eyes, actually there's two separate evolutionary pathways to eyes. And we humans kind of have a convergence of those things. So we got here by two different pathways. I don't know if that's true or not.
Well, yeah, and other animals see things differently because they have a different need for it.
And human color vision is actually not that good. There are certain species of butterflies that can see like 16 million different colors. Humans can maybe a couple thousand. Our ability to separate gray scales is even worse, actually, which is probably related to that whole structure of the eye. What we are really good at is seeing patterns, but that's a different story.
A lot of insects don't see ultraviolet into the ultraviolet, and that's where they kind of operate a lot of their.
Yeah, and I think
what they do is tied in with that.
And I think those butterflies that can see 16 million colors are seeing parts of the spectrum that we can't see. So.
By the way, on another note, I've done this many years ago. I used to, whenever we had open houses, I would ask kids if they see the color in the Ring Nebula, and almost always they would say, yes, it's this color and this color. And you ask adults, and they said, they don't see any color there.
Yeah.
So your eyes do relinquish that color perception over time.
Yeah, I think my eyes are relinquishing both color and clarity. Yeah, I was noticing that looking through the Kessler. Was like, God, my eyes are terrible, But anyway, I guess that's what happens. Okay, so that's a little bit about seeing things, and I also thought I'd talk a little bit about how you find what to see here. And again, I know this is probably stuff you guys know thoroughly, but let's talk about it anyway, unless you don't want to.
There's 3 people online.
Oh,
Who knows who
okay.
they are, right?
Good.
Hi, people.
And this was actually something that I talk about because it was not an easy thing for me to get. the whole notion of the celestial sphere was a little bit of a challenge for me when I first learned it way back when. But the basic idea is that, you know, this gets back to our perception, right? You look up at the sky and you think, and the intuitive sense of it is that there's some kind of a dome up there with all these little marks or glowing objects or something on it. And I think for a long time that's sort of what people thought was actually happening. One of the early theories was that, you know, there was a dome with little holes in it, and that's what the stars were. And of course we know that's not the case, but it's also how, for better or worse, we have come to kind of think about location in the sky. So I thought I'd talk a little bit about the celestial sphere a little bit. And that actually leads us to a couple of concepts that have to do with angles. Elevation and azimuth. So again, we're looking at a sphere here, but it's also kind of useful to think about it as a hemisphere, right? Half a sphere, basically. So if you're standing on some point on the surface here, there's our visual horizon right there, there's our full sphere. You can see half of it, right? You can see whatever half that's above the visual horizon. And if you want to find some object in the sky, you can think about it as a coordinate system of elevation and azimuth. So elevation is, in my opinion, the easier of the two, because essentially what it does is it tells you how far above the horizon you are. So there's a nice natural starting point, right? The horizon. Azimuth's a little bit trickier because it's a full circle, so there's really no natural starting place. But of course we have a system imposed that came about as a result of understanding the Earth's magnetic field. And so in most cases, azimuth is measured from north. And I think in astronomy, it's exclusively measured from north. There are some things, like I'm a climatologist, basically. And so when I switched to thinking about climate, I had to start thinking about azimuth as starting at due east. And there's really pretty good reasons for that. The other change of thinking I had to have was, instead of thinking about the elevation of something, I thought about its angle relative to zenith. So in my mind, I think about zenith angle and azimuth from east, because it's become my kind of go-to way of thinking about it. Astronomy, though, as far as I know, it's strictly azimuth measured from north, elevation measured from or altitude measured from the horizon. And of course, the most convenient way to think about these is either circles or part of circles, right? So the azimuth is a full circle, and we measure those in degrees. So units of azimuth are going to be from 0 to 360 degrees. And then a degree is actually a pretty big unit. There's 360 or 60 of them in 360. There's 360 of them in a full circle. So that means each individual degree is actually pretty big. So they're broken down into minutes and seconds, right? So a minute is 1/60th of a degree, and a second is 1/60th of a minute, and there's 3,600 seconds in a degree. Elevation is also kind of thought of as an angle, but in this case it goes, for the most part, from 0 to 90. So you think about it as elevation from 0 to 90 degrees, which is zenith, the point directly overhead. You can also think about it as 180, but I think in most cases in astronomy it's negative. Zeniths or elevation angles are given as negatives if they are kind of on the other side of the circle. So here's a person, I don't know who made this drawing, but I thought, you know, I'd steal it. There's a person who's looking at the sun, and there's elevation, and there's azimuth relative to north. Here's a little trick that you can use. As I said, you know, there's degrees, minutes, and seconds, and the size of a degree is actually pretty big. So you can use your hand to kind of estimate these. So I learned this a slightly different way. What I learned was that if you hold out one of your fingers, that's about a degree. These people are saying it's your pinky. Of course, this also depends on how long your arms are and how big your fingers are. But as it turns out, most people who have small fingers also have short arms, and vice versa. So it roughly works. I kind of have little skinny, bony fingers, so this probably doesn't work all that well for me, but I'm kind of relatively long arms, so But anyway, a finger is about 1 degree, and then if you hold up 3, it's about 5. A fist is about 10 degrees, and if you kind of hold your hand out like that, that's about 25 degrees. So the moon is about half a degree, about 31 arc minutes. So when I was young, my mother had a friend who had been a fighter pilot during the Second World War, and they were taught, if you had to be careful about the sun, right, because that's where the attacks would come from, and they were taught to hold their finger out and block the sun, because the sun has essentially the same angular size as the moon. One of those little accidents, basically. So anyway, this is a good way if somebody tells you, oh, you're this many minutes of an arc or something away from something. This is a good way to kind of estimate that distance. And also the whole altitude, I'll get to that in a second. The whole altitude and azimuth thing is actually the basis for one particular type of telescope mount too. I'm sure you've probably seen these. There's all azimuth mounts. They're exactly that. They move in altitude, they move in azimuth. Mostly Dobsonians are mounted this way. Other telescopes are as well. The problem with these, of course, and this is where something like this would come into play. The problem with these is that if you want to track something, the sky does not move the way altitude and azimuth moves, and there's reasons for that we'll get here in just a second. So objects and again, I shouldn't say the sky is moving, because the sky is not moving. Objects in the sky are moving. And so if you want to track something with an altitude or azimuth mount, you have to move it in both axes continuously. And that makes that's possible to do. Actually, it's become much easier now because computers can solve this kind of problem really fast. So a lot of professional, very large astronomical telescopes now are mounted this way. Of course, the problem for people like us who want to do imaging or astrophotography is as you move, the field rotates, and of course that kind of messes up your photography. So you can get field derotators now, and of course, again, most of the professional telescopes have very good technology for doing this stuff. But these are the plus side of these kind of mounts. Again, I'm sure you all know this, is that they're very sturdy, and they're really easy to use, and they're compact, right? I mean, if you look at this thing right here, this is this is a smallish one, and yet still relatively large compared to, if you can imagine, an altitude azimuth mounting like this, which in that case, this polar axis right here would not be tilted, right? It would be flat relative to the horizon. And you could replace this entire component right here. I don't know if you guys at home can see this. You'd replace this entire part of the assembly right here with basically just a fork or something very much like that. So, but that's another kind of related to this kind of looking at the sky in terms of altitude and azimuth. How bright things are is actually another kind of thing that is, I mean, partially it's a question of distance, or almost exclusively a question of distance. But there's a relationship between how bright things are and how bright they look that has to do with distance away. And so the relationship between luminosity and brightness follows a square law. Basically, it's an inverse square law, actually, which is interesting to me because gravity does the same thing, right? The force of gravity degrades as an inverse square. And I'm sure there's a pretty good reason for that, but I don't know why both of these basically do. But here's the reason why. If you can imagine, there's a cone of light coming off of an object, basically, that's luminescent, that's producing radiation. The further you are away, the bigger cross section of that cone you're going to be looking at, right? So it's exactly the same amount of energy, but it's spread out over a larger area. And it just turns out that if you double the distance, that area will increase by 4. It'll always increase by a square. And this actually also plays into the magnitude scale, which was another one of those things that kind of, I won't say baffled me at first, but seemed a little counterintuitive to me when I first learned it back in the whenever that was. And of course, when we talk about this magnitude scale, we're talking about the apparent magnitude. So there's the luminosity of something, how bright it actually is, and then its magnitude is how bright it looks to us. So the original magnitude scale goes back a long, long way. This is Hipparchus right here. He invented this magnitude scale. And at the time that he was thinking about this, he basically just divided up visible stars into 6 categories based on how bright they looked to him. And he called the brightest ones magnitude 1, and the dimmest ones, which were the ones just barely visible to the human eye, magnitude 6. And that's why we have this kind of reverse numbering system, right? The brighter something is, the lower its magnitude. Which again is one of those things that it makes sense once you think about it, but when you first see it, why did they do it that way? Of course, where this really got kind of complicated was when it became possible to actually measure the brightness, not just visual estimation, but actually use photoelectric techniques or whatever to actually measure brightness. And of course, the other thing that about that is when telescopes became in common use, it opened up the scale, right? There was all of a sudden possible to see things that were far too dim to see with the naked eye. And so, after a lot of kind of hand-wringing, I think, it was decided that the magnitude scale had to be formalized a little bit better. And the formalization was that 5 magnitudes was a change in brightness by a factor of 100. So a magnitude 5 object is 100 times dimmer than a magnitude 1. And if you take the 5th root of 100, it's about 2.55. So that's the difference between magnitudes. It's roughly 2.5. So a magnitude 2 object is like, I guess what Polaris would be a magnitude 2 star, is going to be about 2.5 times as dim as a magnitude 1 star. Like, I don't know, give me a magnitude 1. Sirius, maybe? No, it would be brighter than that. It's a negative, I think.
Yeah.
That's the other thing that got a little messy on this, is that there were actually things brighter than magnitude 1, so they became magnitude zeros.
First, it's about a 0.
Is it a 0? What's a 1?
Arcturus isn't that bright. What's a
Rigel,
Vega?
maybe?
What's Vega?
Might be a 1.
Vega's minus.
Vega's a 0.
Minus,
Vega's a
yeah.
0 because Vega is
Okay.
actually used as like the index of all this
Vega's
stuff.
a 0?
Yeah.
Mm-hmm.
So Vega's a
Okay.
magnitude 0.
Yeah.
And it was actually used to kind of calibrate the scale. So there's a little formula, and if you take Astronomy 101, you
So
learn.
Sirius is brighter than Vega then.
Antares.
Antares is a 1?
Mm-hmm.
Okay.
Antares.
And so I'm pretty sure Polaris is a 2, although it's a variable, so it's going to vary. But so it would be 2.5 times dimmer, and then a magnitude 3 is 2.5 times 2.5 dimmer, and so on and so on. So here's a few examples there. Venus is almost a -5, the moon, full moon about a -12. Sun is about a -26. You know, it's a super bright thing. People with good eyes, which is not me, can see in some places up to about magnitude 7 if the sky is dark enough. There's probably people, you know, young kids maybe, that can get a little bit beyond that. But generally the naked eye limit's thought to be about magnitude 6. There's Polaris right there. This is the range of the Hubble, about magnitude 28. What do we get at Farpoint? About 21 maybe?
Yeah, 21,
21 and a half, 20,
Yeah.
we were able to get to 22. I mean, this is using camera, but we were able to get to just right at 22.
And that's with the-
Maybe a little bit dim.
The old Tomba arrangement. The
Yeah.
new one should do a little better, right?
Well,
Provided the
I-
sky
I,
is.
I don't know that it will go deeper.
Okay.
I think I'll refer to Russ here because he did a little bit of thinking about this, and he said, you know, you still got, it's based off of focal length, not off of
Right.
how much light you get in quick succession, but if you have enough time, you can actually get deeper using the longer focal length.
And that actually would be, you know, not to renew my plea, but that is the sort of thing I don't understand very well. And if anybody ever wants to give a presentation on that sort of stuff, I would be rapt audience for it, because
What sort of stuff?
I don't, that relationship between focal lengths and, you know, all that is, I gotta admit, a little fuzzy to me.
Well,
So,
and there are other circumstances too that I have to tie in. If you're talking about a theoretical, being able to do a theoretical magnitude with a given focal length, it may take you 3 nights to get that point, but, you
yeah.
know, because you've got other factors and air turbulence and,
And
you know,
haze.
you have a lot of other factors involved.
Aerosols,
It's
yeah.
just theoretically, you could, with the same focal length, you could get to a certain magnitude in any telescope.
Yeah, and these are visual
Do you mean
magnitudes,
aperture?
and there's actually
Regardless
color
of that.
magnitudes
Yeah.
Mhm,
as
yeah.
well. And if you start doing like telescopic photometry and different wavelengths, you get different magnitudes and based on those. So there's color wavelengths as well, but this is just the apparent magnitude. So this is the magnitude scale. All right, so talked a little bit about altitude and azimuth and some of the advantages of it. And one of the nice things about the altitude and azimuth system is it's really easy, right? It's basically 2 really pretty simple angles. The problem with it is, as we said, the objects are not moving either parallel to the ground or perpendicular to the ground. They're not moving in altitude and azimuth, they're moving in both, basically. And that creates some additional wrinkles in actually finding things. So if you can actually sort of look at this, and this is a little bit of a fuzzy picture here, but I think I got this out of a textbook somewhere, so this is a little bit of a scan. Kind of illustrates the idea. So one of the inconvenient things about the Earth is it does not necessarily orbit. Let me back up a second. So it orbits around orbits around the sun in this plane called the ecliptic, right? So, and pretty much all the planets, with a few exceptions, are no exceptions now that Pluto's not a planet, are more or less in the plane of the ecliptic, right? And if you could view the solar system from a distance, you would see it looks like a mostly flat collection of stuff, all more or less in the same plane. That plane's called the ecliptic. The Earth, though, the rotational axis of the Earth is not perpendicular to the plane of the ecliptic. It's not at a right angle, it's tilted. And in the current epoch, that tilts about 23.45 degrees. Varies between about 21 and 26, basically. So if you could watch the Earth orbit for a very long period of time, it would look like it was wobbling a little bit, kind of looked like a little top wobbling. And those 3 wobbles are actually, again, getting back to climatology, one of the things that probably drove glaciation advances, differences in insulation because of those 3 precessional motions. But anyway, from an astronomical point of view, what that kind of means is that the sky is going to sort of move at an angle. Objects in the sky are going to kind of move at an angle. And so if you want to track something in the sky, altitude azimuth mounts don't work. What do work is something like this, all right? So this is an equatorial mount. Basically, it's set up so that you set it at an angle equal to the latitude of where
Hey,
you
Doug,
are.
Can you hold it over so
Sorry.
people online can see?
Sorry. Yeah, so you set it at an angle equal to the latitude of where you are.
They can't see that well.
Can I see it?
There you go.
Okay, sorry. So you set it at an angle equal to the latitude of where you are, and then you only have to really track in one direction, basically. So you don't have to kind of do this 2-axis tracking business. But it does actually also create, thanks Justin, it also does create a complication in finding things. The other thing that creates a complication in finding things is that things are always moving in the sky. And so the system that has been developed to kind of navigate the celestial coordinates has to take all that stuff into account. And this is where, the geometry gets occasionally a little bit kind of fuzzy, I guess. But what works for me, anyway, and again, this is something that it took me an embarrassingly long time to get this. So I'll admit right now that, this was something that baffled me for a long time. What works for me is to try to think about it as an analogy with latitude and longitude. So navigation here on Earth is complicated by the fact that we're on a sphere, we're on the surface of a sphere. You can't use rectangular coordinates on a sphere for very far. You can use them real easily, and by rectangular coordinates I mean coordinates that cross each other at right angles, right? You can do that for a little ways. So there's systems of coordinates that are rectangular. But if you want to do it over the scale of an entire planet, you can't do that. So what we have is a system that essentially is based on circles again. So latitude is distance north to south, right, and longitude is east to west. In the terrestrial coordinates, latitude has a really natural starting point, the equator, right? So you can always say, okay, if I'm on 0 degrees, I'm on the equator, all the way up to 90, and I'm at one pole or the other, and it don't get no bigger than that, right? Like Stephen Hawking used to say, there is no, being outside the universe is like being north of the North Pole. There just is no such place. That part's easy. So your latitude is always going to be a number whose absolute value is somewhere between 0 and 90. By the way, if you ever get a chance to go to one or the other of the poles, you are standing on the only place, well, you'd have to be the South Pole. If you went to the North Pole, you'd be standing on ice or water. You're on the only place on Earth that you can identify with one single coordinate. And if you take one step away and then walk a circle, you have walked all the way around the world. You've touched every single line of longitude, just as an aside. So there's a nice, easy starting point there. What's a little trickier is where do you start the longitude system? Because longitude is 360 degrees, right? It's a full circle. So that problem kind of had a lot of different answers for a long time. Of course, now we have sort of standardized all that. The starting point of it is a line that passes through the Royal Observatory at Greenwich, England, right? So that's 0 degrees longitude. There was a big dispute for a long time between 0 degrees longitude Greenwich, 0 degrees longitude Paris, and 0 degrees longitude Mecca. And finally, I guess the British just decided we're the world's dominant naval power. This is how we're doing it. But anyway, that's how this system came into play. So the system of coordinate finding in the sky is similar to that, except for one really important thing. With geographical coordinates, we're standing on the surface of a sphere. With celestial coordinates, we are standing on a surface looking up into a sphere. And so you have to kind of think about it. The other thing is that the coordinate system is based on things that are moving, right? The Earth moves. So that produces some complications, and I think those complications are what always sort of baffled me a little bit. So any of you that get this stuff any better than I did, if you want to pitch in, I would be more than happy. But basically, the whole system boils down to these things called right ascension and declination. So declination, I think, is pretty easy. It's basically just that coordinate. It's the elevation coordinate, right? It's complicated by the fact that it starts at the Earth's rotational horizon, essentially the rotational plane of the Earth, which is not the visual. How do we put this?
Equivalent of the horizon.
That's not the visual equivalent of the horizon, right? Because the horizon is different depending on what latitude you actually are at. And so you can have negative and positive declinations. But that one is, I think, relatively simple. It's right ascension that is weird. Because, in the case of longitude, it was just decided, right? It's going to be here. There's really no easy place to decide where to start the system of right ascension. So basically what the solution to that was to, okay, so kind of translating this diagram, here's an extension of there's the celestial equator right there. Here's the ecliptic, that's the plane in which the Earth is orbiting the sun.
Or the rest of the planet.
And where they cross, at the vernal equinox point, is where the system of right ascension starts. So this little thing right there actually has a cool name. It's called the first point of Aries. And why it's called the first point of Aries, I'm not really totally clear on. But it's where the path of the sun, it's essentially the position of the sun as it crosses the celestial equator going from south to north, which is the vernal equinox, right? So it's the spring equinox. So that's where the right ascension point actually starts. Where it actually is somewhere in Pisces, right? So the zero of right ascension is in the constellation Pisces. And so why it's called the first point of Aries is totally
I
unclear.
think
Do you
it
know?
used to be the first point of Aries, and it's through, the
Precession.
long recession.
It's
It's
kind
changed.
They still refer to it that way, though. I remember,
Yeah, I
Dr.
know.
Dietz back in the day saying it's the first point of Aries.
Yeah.
I was like, what the hell?
They ought to rewrite all the books.
Anyway, so that's where the right ascension system
Through
starts.
another planet even.
So right ascension is the distance east from the first point of Aries, and declination, I should back up here for a second. Declination, oh, okay, I got a little ahead of myself. So declination is an angular distance, and because it's an angular distance, it can be measured in degrees. So here's a kind of a representation. There's the celestial equator. You want to find the celestial equator, the easiest trick I know is to find Orion, because the belt of Orion is almost exactly on the celestial equator. That star right there, whose name I don't know.
Mintaka.
Mintaka is almost exactly on the celestial equator. So if you can see Orion, that makes it pretty easy. Orion's also kind of a cool constellation because it straddles the celestial equator. So some of the things in it, like Betelgeuse, for example, 7 degrees, 24 minutes north in terms of its declination.
Now,
Right.
celestial equator is, am I right, that's the path of the planets?
Yeah,
Yeah.
within
Also.
a couple of
So
degrees.
the planets, wherever they are basically following the celestial
It's
equator.
a little off.
A little off.
A little
yeah.
off, but
Yeah,
there's
close
a
enough.
range.
because they are kind of at angles to one another. Actually, you can kind of see
I think
that
it's
on
about
the,
a 6 degree.
you can see that here.
space
It's
or
they're,
something.
the planets are going to be line up along the ecliptic, right?
Yep.
So yeah, but it's pretty close.
Hey Doug,
Yeah.
go back to that. I think this may help with some people online. So when you're having your telescope like that, so then your right ascension is
Yeah.
One like that.
going
Yeah.
back and forth, and then your declination is you're moving your azimuth up and down.
Justin,
Yeah.
people may not know where the telescope attaches to that.
Well, your telescope is gonna be right here on the tube, and your weight will be right here on the bottom side, and didn't bring it.
Mhm.
But basically, your tripod then is down below. So that's probably the easiest way I can,
And the latitude is going to adjust right here, right? You
Yeah.
can change the angle of this axis right here. So this axis right here would have to be at the same angle as the latitude.
that's your
of the
elevation of your location.
location. The latitude.
Right.
Yeah,
Yeah.
yeah, latitude of our location.
Yeah. Which must make setting up an equatorial mount at the equator kind of interesting. Wouldn't it just default to being alt azimuth then? Yeah,
Straight up and down.
yeah, yeah.
East-west.
That's one of the things that always struck me when I was near the equator was watching things go straight up instead of on an angle.
Yeah.
Anyway, so that's the system of right ascension and declination. So here's a couple of examples. So that would be, that's Rigel, right?
Yes.
So I gotta ask the expert. So that one's gonna have a negative,
You'd be pretty safe in saying that, I guess, because
yeah.
safe's just on the other side.
Yeah, so it's gonna have what about maybe a -8 declination. There's Sirius, -16, and so on. Okay, so that's the declination thing. So right ascension again is kind of reference to this vernal equinox right here. And so right ascension is, you can't, because it's on a continually rotating frame of reference, you can't use degrees, you can't use angular distance. What you need to use is time. So what this basically says, here's again Betelgeuse, its right ascension is 5 hours and 55 minutes. which means that it's going to rise like 5 hours and 55 minutes later than anything that's on that 0 point rises. And so that's how that coordinate actually works. So it's the distance east in hours, minutes, and seconds. That's what I guess I always had a hard time wrapping my head around, is now we're thinking in terms of distance or rising times. It's going to be the distance east from that first point of Aries, that location, that kind of, and one of the things that makes it tricky is there's really nothing there, right? You know, like on Earth, the Polaris is right there at the point of north, right? There's nothing there to point to and say that's where the system starts. So anyway, that's the right ascension. And so you consider those two things together, and that gives you a coordinate that's going to not change through time. So objects have the same right ascension and declination. It also helps you figure out when things are going to be visible, right? Because you can kind of figure out those times, those rising times and stuff. Okay, so celestial coordinate system. We talked a little bit about the ecliptic, and so it's always kind of useful, I think, to know the constellations that lie along the ecliptic. Of course, they're referred to as the zodiac. There's actually 13 of them.
Yes.
You know, there was, for years, I guess the zodiac was 12, and of course, people thought you could divine a person's personality based on that. I have severe skepticism on that. But so now Ophiuchus is considered one of the 13th zodiac. I don't know if the astrologers taken that into account.
They don't, but part of it is because Ophiuchus technically is in that, it's just such a short time that where it actually crosses the ecliptic there. And it's something like 13 days. It's way less than the rest of them.
So its
Just the
month
way
is
it's drawn.
really short.
Well, yeah, it's you'd have to be right, yeah. So I think that's one reason they just kind of, and they also would look at the constellations, and of course they had stories and stuff, and Ophiuchus goes so far up there. You know, if you look at the other constellations, they tend to straddle, you know that, and Ophiuchus is just sort of like touching his toe into it, so they tended to kind of ignore him.
Yeah.
Yeah.
And of course, if you're watching the planets, they would be roughly along this ecliptic here, which kind of leads to this notion of them being in a particular constellation,
Yes.
of course, which is one of the things that the astrologers and the astronomers keep track of. So if you want to see the planets, then you look along the ecliptic. Sometimes they talk about the racetrack. Is this a term you've heard before? And that's the path along the where you're going to tend to see these. And like right now, the planets are all morning objects, right?
Pretty much, yeah, they're starting to come around.
But they'll start to become evening objects.
Well, because they move at different speeds. They orbit at different rates, so then they'll start kind of moving apart a little bit more.
Right. So there's the racetrack, and you can see it kind of goes through those constellations of the zodiac along the ecliptic. So if you want to look at planets, there's some definite timing issues that make them easier or harder to see. And it kind of depends on where the planet actually is. So planets, are divided up into the inferior planets, which I think doesn't necessarily mean that they're lesser. It just means that they are closer to the sun than we are. So of course the inferior planets are Venus and Mercury. And then the superior planets, which are the one furthest away. If you want to see an inferior planet, the best time to see them are what are called the elongations. They're the times when its angular distance from the sun is the greatest. When they're at their conjunctions, you really can't see them. They're either lost in the sun or behind the sun. So you really, those conjunctions are periods when things are lined up, basically. You really can't see them. So that's the reason why if you want to see Venus or Mercury, you either have to get up early in the morning, or I guess Venus can be it can be an evening object.
Yeah,
as well.
it can. It can.
Yeah.
It's just that it's not up all night
Yeah.
as you would something else.
But Venus is a lot easier to see because its biggest elongation is like 42 degrees or something like that. So it gets much further away from the sun. Mercury, its biggest elongation, which just actually happened in March, I think, is it's like 21 degrees or something, so it's never very far away from the sun, which makes it tough to see. So I've personally never seen Mercury. I don't know if any of you guys have, but I personally, it's the one naked eye planet I've never actually seen. If you want to see the superior planets, the best time to see them is at opposition, when they are as far away from the sun as they can get and essentially lined up with the Earth. They are not visible at conjunction because the sun's in the way. Okay, so how to find your way. These things, again, are something you probably are all pretty familiar with. There's actually really good, just taking one of these things out, a planisphere, and playing with it is a really great, I think in some ways that's how I finally kind of got right ascension and declination, because the grommet, the little thing that it pivots on is Polaris, right? And it's kind of like, at first it's like looking at things backwards, right? This way, this way means you're going towards the horizon, basically. So there's the celestial equator, I believe would be that one right there. But it kind of, I think, it made it a little clearer to me, at least, how the right ascension and declination thing actually worked. Of course, we live in the age of technology now, so you can get this thing. I don't know about you, but I have never had much luck with Star Walk. I sit there and hold it up and do that, and it doesn't work very well for me. What it's good for is kind of figuring out in general what direction I'm looking, but I have a really hard time identifying actual things on that. I don't know, maybe you guys had more luck than that, but
I have a story that I've told before. We were out at Farpoint, and we had a group out there, and somebody said, "Where's our tourists?" And everybody pulls out their cell phones and starts looking all over. And I looked at everybody and said, "It's right there." I just pointed at it with my little finger right up there where it was, because they had no idea, where the sky was, but they pull out their phones and start.
I'll tell you though, one of the most interesting things I can ever remember seeing was, it was at that trip to Chaco, and they had an interpreter out there. And I don't know what this person's background was, but they were extremely knowledgeable, and they had a precursor to this on an iPad, and they had a laser pointer, and they were like, okay, look at, and it was like, wow, it all makes sense, which was a sort of, the scales fell away kind of experience. But anyway,
The guy looked like Johnny from WKRP.
Johnny
He looked exactly like Johnny as far as, because I was out there too.
Yeah,
And
he did.
He was kind of hippie-like.
Now that you mention it, he
Yes.
did. He looked like Howard Hessman.
Yeah, we saw the same guy.
Okay. Well, wasn't it great though? I mean, did you see him do his thing?
Oh yeah, he is doing his stick. Sure.
Did he have the pad?
I don't remember him having a pad at that point.
It was incredible. I met another fellow once who was a friend of my sister and brother-in-law, or a friend of theirs, who was an astronomer, and he lost his job because of something. He was working on something on the New Horizons mission. Anyway, things changed, and he lost his job. So he ended up getting a job for a while, I think, working on a cruise ship as an interpreter. And he was, now he's of course back to working at. But anyway, he did sort of the same thing, That was it was just a really incredible experience, though, to listen to Dr. Johnny, if you were give his description of the heavens. So anyway, there are these tools for finding your way, but I guess I've kind of, in this case, would be an advocate of kind of old school, getting one of these things out. And that brings us to finding our way and the fine art of star hopping, and I figured at this point I would turn it over to an expert in star hopping. So, Jan?
The best way to explain this is, if somebody were to ask me how to get to Farpoint Observatory, unless they're coming from the south, my directions are as follows. Go to the intersection of 53rd and Auburn Road, and then head south. And you get to the city of Auburn, you're there when you see a Dollar General on your right. Then you keep going through the city, not very long, but then when you see Gambino's on the right, and there's a convenience store on the left, just beyond that is a street. I think it's 8th Street there. There's a sign before that says Farpoint Observatory, Mission Valley Schools. So you turn on that road and you head west for a long time until you get to the point where the road itself curves left. After that curve, you've got about 2 miles until you get to a road that will go to the right. You'll see the signs that say Mission Valley and Farpoint. You turn right on that one, and then you keep going for a while, and you'll see a water tower coming up on your left. And then after you see the water tower, you see the school districts over on your right. So you go, I heard that.
The library will close in 15 minutes. If you need to print a document from your computer or use the copy machine, please do so now. Children who need to call for a ride home need to do so now at the customer service desk.
Okay. So anyway, you see the water tower coming up on your left, then you'll see the schools on your right. You go just beyond the water tower, you'll see a gravel road to the right. You go about half a mile there to Farpoint Observatory. Now, if you take that same procedure and put it in the sky, it's called star hopping. Except instead of saying, for example, Gambinos and Kurt's Curve and a water tower, you will say the 2 pointer stars in the Big Dipper, and then go this way, and then if you keep going a little bit there, you'll get to Cassiopeia. It's the same concept. Star hopping, basically, I started off with these. These are the 5 circumpolar constellations. And Ursa Major is the Big Bear. And most people know the asterism inside the Big Dipper. So what you do is you start with the pointer stars on the far end of Ursa Major and follow those to your start at the bottom of the Dipper and go through the top one there and keep going, and you'll run into the North Star, Polaris. And Polaris is at the end of the handle of the Little Dipper, which then curls around there. And then if you look between the 2 dippers, you'll see a line of stars that is the tail of Draco the Dragon. And that line of stars goes down for a little ways, then it curves up the other way, and then it does another U-turn right around there. Keep going. And then you go up, keep going where it says Draco, and keep going, and then turn around. It does a little turn right there as he turns, and then you come down to a little shape that makes up the dragon's head. And the 2 stars at the end of the dragon's head look like they're bright, the dragon's bright eyes. That's Rastaban and Eltanan by name. Now, if you go back to the dippers, and I usually start at Polaris. Start the Big Dipper, go to Polaris, and then just keep going to your left and slightly up, and you see an M or a W. That's Cassiopeia. And then in between Cassiopeia and Draco, you see this little thing like a 5-year-old just drew a house. That's Cepheus. So that is star hopping around the 5 circumpolar constellations. And circumpolar means around the pole. And from where we are, you can always see at least some of those. In like the winter, Big Dipper gets really kind of low, but you can always see some of those constellations in the northern hemisphere. That's star hopping through those 5. Okay, next slide. Another one that's really well known is if you start at the Big Dipper, and there's a little saying, and you follow the handle. You start at the bowl and follow it, and it says arc to Arcturus and spike to Spica. Or some people say speed to Spica. And Arcturus is the brightest star in Votates the herdsman. And you can recognize that as looking like a slightly dented ice cream cone. And then when you go down to Spica, Spica is the brightest star in Virgo, the Virgin, which is one of the stars of the constellations of the zodiac. If you look slightly to your right, go to the edge, the right edge, Doug.
I lost the arrow there.
Yeah, okay. If you keep going to your right, you'll see a backwards question mark. That's Leo, the lion. And he points to, you can see there's a right triangle, and that's the back of Leo. So you follow along that way, and you can follow the constellations of the zodiac, and that's all star hopping. See that's a question mark. And these are all things that are visible around this time of the year, kind of like in spring. So then I put one more on there that shows a star hop in the winter sky. And as you mentioned earlier, Orion is really easy to see. You've got the 3 belt stars, and then you've got the 2 bright ones on the top and the bottom. If you follow the belt stars from right to left and just keep going, it points, oh wait, Start from right to left, keep going, it points to Sirius, which is the brightest star visible from Earth. It's called the dog star because it's in Canis Major, the large dog. And another thing that you can also do, which you can't really see on this slide, but you can also use Betelgeuse and Bellatrix, and they kind of point kind of between that, and then the belt stars going to the right points to Taurus, the bull, because they're all up there. And one of the things I do when I have people out there is I add stories to things. So what I tell them on this is that Orion was a hunter, and he had a hunting dog, but they weren't very good because you got the hunter and there, and right between them is a rabbit, and they're paying no attention to it at all. And that's the way people, that's one of the reasons when I do this, I put those stories in there because it makes people remember. And then also, if you start at the middle star and just go straight down, you'll see a fuzzy patch that is the Orion Nebula. And another thing, this takes a telescope, but if you go to the leftmost star and just kind of look in that area right around that leftmost star, that's where you find the Flame Nebula. And the Horsehead Nebula is also there, but it's very tiny. People don't realize how small that is. The Flame and the Horsehead you can get in one field of view, but it's very, very small. So that's something you need some magnification for. But you can find a lot of different ways on the stars to just use one star from the other, just like Dollar General to Gambino's, and that's the whole concept of star hopping. And there you go again.
That's a better picture.
Mm-hmm. Yeah, you can see the Orion Nebula really well there. And even from the city, I'm able to make that out as a fuzzy patch. So that's a real quick idea of how star hopping works.
Okay.
You might connect to Members Night, and they can come out and star hop with us at Members
That's
Night.
right.
Yes.
And
That's
and then when I have a group out there, I always show them the concept of star hopping. That's how I learn most of the sky.
And I mean, I can't speak for anyone else, but it would be real interesting for me, some members' night, to go out there with Planisphere and just kind of do this stuff. Because,
Mm-hmm.
you know, my knowledge of the sky is kind of C+, B-, to be honest with you. So,
Yeah, for so many years, that's all I had. So I've gotten pretty good at looking at that.
all righty. Well, I guess we're about ready to
Yep.
kind of run out of time here. So thank you for coming, and thank those of you at
Yes.
home for